Hello and welcome to lecture three on day two. Um, so we just saw an example of Hello World and Chisel, and we got, a simple design, close the loop, right? That was the whole goal. That's the whole logo for this course. Wrote some Chisel, got to see both simulation, got to see Verilog, see the output of what we're doing. And so today we're actually going to dive in much farther depth, and we're going to go ahead and see combinational logic. And in just the course of this next lecture, we're going to cover like 80 or 90% of the combinational logic that we need to worry about for Chisel for this course. And then in the lecture next week, we'll cover all sequential logic. That's a lot of logic involving registers. So actually, by the end of those first four lectures, you'll be able to do most things you can do in Verilog in Chisel. And then from then onwards, we'll start moving on to things we can do in Chisel that are much harder to do in Verilog and kind of take advantage of the full flexibility and power. So we're kind of still getting warmed up, but it's good. And so you kind of see the same model we saw before. We're kind of this intermixing of a little bit of Scala, a little bit of Chisel, a little bit of design use of that, and then close the loop, actually use it, and then we'll move on to something a little more sophisticated. And that might involve a little more Scala, a little more Chisel, a little more design use. Um, we just had a conversation about Verilog during the break. I'm trying to remember what I was supposed to talk about. Yes. So one detail which maybe is worth repeating in case people aren't aware. The tool Verilog is most commonly used for, that is to describe hardware to be passed on to a CAD flow to actually turn into hardware. In other words, synthesis, placement, routing, etc. That's actually not what Verilog was designed for. So Verilog was originally designed to be a language to describe hardware for sake of simulation. And the conversion from that simulation language, or in this case RTL, to a hardware with synthesis, that was developed after Verilog was made. And so as a result, Verilog has constructs in it as a language that can't be synthesized, right? Chisel, having the benefit of hindsight as a language, everything in Chisel is synthesizable, right? It is a hardware construction language. Now, our generators will intermix Chisel with Scala. So, of course, the Scala, which is, a program, that's not going to go into hardware. But the Chisel that's actually being done, that's all synthesizable. So, it's a little bit of a different thing. Whereas Verilog was designed a long time ago, so it was designed for simulation. There are certain constructs in Verilog that aren't really synthesizable. In Chisel, everything is synthesizable. And we also have the flexibility of a program wrapped around it. Let's go ahead and see how this plays out. As I said before, today we're going to kind of cover combinational logic. Along the way, we'll also talk a bit about parameters and conditionals. Okay, so once again, fire up the old notebook. Good to go. So in the last lecture, we talked about things like, logic gates, arithmetic, etc. What about if you want to do a mux? A mux or a multiplexer, right, is a way to, given an input selection signal, choose between two inputs for the output, right? So, if select is 0, we get input 0 connected to the output. If select is 1, we get input 1 connected to the output. And so in Chisel, we can simply just declare that by saying mux, give the selection signal on the two inputs. One little wrinkle to be aware of, input 1 is first. So why would they do that? At first, it seems a little counterintuitive. Why would you go 1, 0 rather than 0, 1? The reason why I did that is actually it's very similar to a lot of other languages. So, for example, if you have a ternary statement in either Verilog or C, if a question mark, it's condition, question, true case, colon, false case. If true, true case, or false case. That's kind of why they're adopting that syntax. Um, it is a little bit surprising to some people. I don't blame them. How's that actually in code? We have some on the right. We can go ahead and, once again, our boilerplate, set up a module. We call them mymux. We have our IO, our inputs and outputs. We have three Boolean inputs, right? The select signal in 0 and 1. Our output, which is, a single Boolean signal. And then what is the actual mux? Like we just talked about, right? We have our select signal, our two inputs. So in this code block, we're both going to declare this module and print Verilog to kind of see what code actually gets generated. And we can see, once again, that the Verilog is pretty similar to the Chisel, right? There's an assign statement here, taking the output to a mux. In the case, the way Chisel chose to do it in this case, it actually uses the ternary statement in Verilog, like we're talking about, and that's why having the in one first kind of makes sense. Cool. Now, you can imagine hardware with a lot more situations you might want muxes that are just a simple two-input mux. And if you're curious, there is a variety of additional muxes available in the Chisel standard library. So if we go to that link in the documentation, hopefully it's the right browser tab. Yes, it is. We can see, for example, here is a mux 1H. 1H is short for one hot. We will come to that in a few lectures. I'm just kind of trying to alert you to this exists, right? There's a variety of muxes. There's a mux based on cases. So there's something called a case statement in Scala. You can use that functionality actually in the mux generation. So there's a few different muxes available in the library. You kind of can scroll through and see things in the API. Cool. Questions so far? Okay, then let's have kind of this little game of go back and forth from different languages. So what about Scala? We've seen so far, we keep declaring things called class. And these are actually objects. They're actually a class, right? These aren't even functions. These are a class. And so why do we keep doing classes? Well, the way Chisel implemented, it uses inheritance to do a lot of things it does under the hood. And so yeah, we need to talk more about classes. So when you declare a class in Scala, you say class, give it a name. What's interesting is you also immediately follow it up with a argument list. And so in some ways, this class declaration looks almost like a function, right? It's kind of, the name and then the argument list, and there's a body. And this body for your class can have arbitrary code. It doesn't just need to be declaring members and methods. It can actually also just have arbitrary codes. In this case, we have, name is created. We have a print statement. And then when it comes time to actually create one of these instances, we just go ahead and say new, the name of the class, and then we got to fill in those arguments. So let's go ahead and run this code real quick. And yeah, we can see, sure, we declared this class. So you can see in the output here, we have kind of two categories of output. We have what is the interpreter kind of doing and what is actually being printed to standard out. So the interpreter, for this first line is, yeah, you defined my class, great. But in terms of what the standard out is seeing is the evaluation of creating this, it creates name. It also calls this print command, which of course, created, and then the argument, which came from up here, yeah, created MC, boom. And then later on, we have this other print statement, which prints this field, this member within the class. So you can see the fact you can kind of reach in and grab that field. That's because, by default, things are all public scope. Cool. Questions so far? Let's go ahead and start tweaking this, right? So, common things that might happen. Well, what if I don't, decorate the class? Nope, I need to have the arguments. Okay, sure. What if I say I want to change the value inside of the class? Also going to yell at me because we define this as a val, right? It's assigned once. Oops, that's hopefully not bad. We'll see what happens. And then, yeah, so if I make it a var, sure, I can change the name. But once again, you'll see throughout this lecture that actually having val will make life a lot better. Okay, so we shouldn't reassign a val. What if I want to, so we can definitely print out the fields. These are all public. What about the arguments from when it was created? For some reason, they made this by default private. So if I try to print one of those, it's going to yell at me. And it's going to give, rather than saying it's private, it's going to say it's not a member. However, if I was to go out in there and just say val, that will make it public. And so much of the time, we don't really need to read the arguments again, so I don't even bother calling them val, but every now and then you may want to read that argument later on, so sure, you can go ahead and toss on that val. Oops. Cool. All right, let's go ahead and make this code work again and move on. So now that we have the ability to add arguments to our classes, let's go ahead and use that in Chisel. So we had this mux, and rather than being a 1-bit bool as the type here, we can get just a little bit more flexibility and take in a width parameter, right? So now our class has this parameter W, which is the bit width of these buses, right? These are W bits wide for each input and W bits wide for the output. So sure, we can go ahead and declare that. We recognize from the prior lecture, this whiffs and chisel are their own type, and we make them with dot capital W. So sure, we declare, these uints are all of that width. We have the mux like before, and let's go ahead and print out the Verilog. Sure, we gave it the width 8, and we can see, yes, 7 to 0 down here. It's a 8-bit mux. Of course, this, can do whatever we need to, 4-bit, heck, even 1-bit. You can see in this case, Chisel Smart recognize, okay, it's only 1-bit wide. I don't even have the bus notation. Because they go to 2 bits wide, so I'm going to go ahead and put in the bus notation for us. Sure. Um, cool. Yes, question. Oh, great question. So, how big are these bools in memory during the program? Um, that's a good question. I suspect, as you suggested, much bigger than 1 bit. Because they're an object, it might actually even be even 64 bits, something like that, probably, because it probably actually has some sort of additional metadata. Um, it's a good question. I think it's probably around like that. I would suspect. Remember that, of course, that a bool in Chisel is a type we're going to kind of be passing around. We'll see this a little bit later in today's lecture of what that means in terms of looks and memory. But let's say instead of bool, if the question was how big is a boolean in Scala, I think the answer is probably 64 bits, but I'm not sure. Yeah, yeah. So the way to think of it is, if you want to do multiple, if you want to do a multi-bit signal, UInt's the way to go. Um, there are times where you have a collection of bools, like you have, n bools. That is totally a valid thing. There's a lot of reasons why it comes up. We'll see that in a few weeks. But typically, when you use a bool, you want that entity to be 1 bit. And you're kind of treating it as 1 bit, viewing it as 1 bit. Technically, in the Scala program while it's running, yes, it's probably bigger than 1 bit. But from a designer's point of view, yeah, when you use a bool, that's be something you tend to be 1 bit. If you want to be more bits, usually uint's the best way to go. Good questions. So I'll show yet another example on this slide of an example of why it would be good. Actually, no, I'm gonna wait another slide. Sorry, I'm gonna save that commentary for another slide. I always want to show you why to keep using val. Um, we'll see that in another minute. Okay, let's say we're doing in Scala. We've done already some amount of chisel. We haven't talked about if or else statements. And guess what? Scala has if or else statements. It's the way you expect. If condition does the true case, else there's a false case. You can use braces to mark the cases. If it's only one line, you can not bother with the braces. Um, and so you can see, for example, on the right, we have this little tiny test case, very trivial. Sure, we have the condition, we set the true, and so, of course, this if block, I can comment this out temporarily, is going to just say, yeah, it did the true case, right? Make this false. Yeah, we'll go down the false case, no problem. Now, one thing that's a little bit different in some other languages is it has kind of this style from a functional programming language, in which case, for a really simple thing, not only can we eliminate the braces, the if statement itself actually returns something. So rather than just being do this code or versus do that code, there's actually a value that's associated with the return statement. So this if, in this case, is going to be true, it's going to go to the true case. The last statement in the true path is what it's going to return. So this is going to return 3. So as a result of this execution, X has the value 3, or you have the value 4. So this style of coding is very common in functional languages, where everything kind of has the return value, so to speak, even an if statement. In other languages like C, you couldn't really do this, right? And C, if controls the control flow, but it's not really a notion of how it impacts the data flow. But here in Scala, you can do that. And so you can do some nice things. You can kind of have this conditional inline, very tidy. And this also answers the question people will say, oh, well, what if I want to create a variable and I have to use a val? You can tell me to use vals, and vals are only right once, but I want to have it be either A or B. Well, you want to be either A or B. The way you do that with a val, with a single assignment, is to have this if statement kind of all in one line. And so yeah, so it's a really simple condition like this. Keeping it all in one line and just tidy. It's actually recommended by style guides because it Makes life easier. Yes. Good question. Yeah. So in Scala, indentation and spacing do not matter. So it's pretty clever how it's able to deduce the statements. There's no semicolons. There's no spacing constraints. Or there's no white space constraints like Python. So it's pretty clever how that works. And so that's why you get spoiled. You learn a new language, you find out it has semicolons, it has white space requirements. You're like, what are we doing? Right? Like we don't need to worry about that. That being said, I mean, as you can imagine, as a best practice, your code should have certain indenting styling to it. There are tools for Scala, like Scala format, which can go ahead and auto format your code and that kind of stuff. Cool. Okay, so now that we have if else, and I showed you mux a minute ago, what are these two things? Let's kind of appreciate you're going to use both, and it's kind of distinguish the difference. So a mux is actual hardware, right? This is doing conditional selection in hardware, right? So when we actually generate the circuit, there is going to be a mux, there is going to be the wires. So it kind of has both pathways there, and that's all there. So the choice of what is selected, that is done based on the inputs as the hardware is executing, right? So we're generating hardware for all of that, and then the hardware's behavior is going to be determined as it's being used based on the inputs, right? In this case, we're doing absolute value. So of course, if the input is less than zero, we can kind of do this all within the mux statement directly. Well, if it's less than zero, then of course we should negate it to get the positive value. And if it's not less than zero, then we can leave it alone, right? So you can kind of see how this is both done in Chisel as well as the circuit here. Now, if I use an if statement in Scala, that's also useful, but it's a very different thing. So remember, part of what we're doing with these Chisel designs, we're not just writing hardware designs, we're writing hardware design generators. So that generation step is an important part of the realization of the hardware. So our Chisel program runs, and as it's evaluating itself, it is generating the hardware, right? And so in this case, if I have an if statement, that's going to impact the execution of the program and consequently the hardware. But the hardware itself is not going to be at all conditional, right? If I have invert set to true, invex, we set to negative x, so then it'll always be negated. If invert is false, it'll just pass x through. So invex will just be um, the x value, right? And so this is a way to, in your generator, be more sophisticated, right? You can imagine your generator based on the parameters given to you by your user. We just covered parameters a minute ago. You may want to generate some things in one way versus another way. With an if statement in Scala, you can select the hardware you're doing. And that's different than putting a conditional execution into the actual hardware itself of a mux. So depending on what you're doing, you kind of want one or the other. Yes. Yeah, so exact great question. What happens if I put an if else statement inside of a module? We'll have some examples later today, but the short answer is that whatever the if else evaluates to, that goes into the hardware. So at the time that code is evaluated to program, that if else is going to choose a certain thing. In this case, the if else is going to either select negative x or x. So that's going to be evaluated by the program, and that's going to, whatever that result is, that's going to be the thing that gets put into the hardware. And the hardware is always the same from then on. So the hardware is not going to be conditional. The hardware is static, unchanged. It's wires or whatever. But the program that generates it can be flexible. So normally the goal is to, I'm not sure I'm answering your question. I understand your question, so I'm asking you to clarify in a second. But normally when writing hardware, the goal is to have a certain understanding of what you're getting, right? And so um, Chisel, despite all the, me hyping up how flexible and powerful it is, at the end of the day, every piece of hardware we're describing directly, right? We're saying, hey, I want this logic gate, I want this mux, I want this register. Aren't the registers today, but obviously we'll use them. And so you're saying exactly what you want. Now, the other languages are high level synthesis, HLS. There you kind of say, I want somebody that does this computation, and you give the tools a lot more freedom to say how they want to do it. And the tools can choose how much to pipeline, they can choose how much parallelism and that kind of stuff. And so Scala, at the end of the day, is still a very literal language, right? When you say I want this hardware component, you will get that hardware component. The productivity benefit comes from the fact of when you want to change the structure of those hardware components, you can do that in a programmatic way with parameters. I don't know if that quite got to your question or, okay, great, thank you. Cool, okay, so let's go ahead and put these together. So you may remember from the last lecture we talked about this notion that, our generators we talked about, it's a program, right? And so yeah, it's a program that runs, and as a side effect, we are getting this circuit, right? This is, thing that comes out. So uh, one place I kind of spend time in today's lecture as well as in future lectures is trying people to kind of thinking about this additional step in the hardware generation process, where it's not just write RTL, give the CAD tools, it's write a chisel generator, the generator runs, that circuit's turned into the RTL, and the RTL then goes off to the CAD tools, right? So that additional step of having this program running is a key sting, right? So they kind of keep saying over and over again, right? Your chisel design is a valid Scala program. All these things we're using, all these things we keep talking about, like a module or a wire or a mux, all of those things are actually components in a chisel library, right? And chisel library is just a Scala library. And so what's happening is, as your program's running, under the hood, it's building things up. It's instantiating things, connecting them. And then at the end, your program does what's called elaboration. That is, it goes through this in-memory partition to have your design, and it turns it into a circuit. And that's, sort of the fertile file we're talking about, right? And so you may have noticed earlier I was talking about things like, oh, well, you can't just have hardware by itself. It needs to be inside of a module. Now you understand why it needs to be in a module. It needs to be in a module because of this under the hood business of the chisel library kind of understanding what you're doing and connecting things up the way we want them to connect it up. To have that context, you need to have that module wrapper. Um, so really, what does this boil down to? Well, the chisel components are actually all hardware family. Like I said, it's a hardware construction language. So things like logic gates, wires, registers, modules, you name it. These are all things you can point to in a schematic. These are all real hardware, right? Um, Everything else in your generator, that's Scala. That is, how do we actually put those things together? So really, it's a matter of thinking about what chisel components they want to instantiate and how they want to connect them, and then using Scala wrapped around those instantiations to do the connections we want. And so that's kind of the key point, is we're using Scala to help us programmatically instantiate and connect these components together. You can think of this as almost like meta programming in a way. And what does it look like? Well, actually, when you're writing Chisel, in a way, you kind of are thinking about things spatially, right? So with Chisel or even Verilog, right, you're thinking about describing the structure of a hardware circuit. That's what you're doing. Technically, in Scala, with Chisel, you're actually making a program that generates that circuit, but still, same idea. You're thinking about what is a spatial component I want to build, versus when you normally write software, you're thinking about, steps, right? Sequence of steps. In this case, less about sequence of steps, more about what is the physical thing I'm trying to build and how do I go about describing that. And we've seen so far some very, very simple chisel modules, which are, a single logic gate, a single mux. As this quarter goes on, we'll get more sophisticated. And the more sophisticated ones start seeing the power of chisel. We go ahead and use things like, loops and function calls and objects and start making much more sophisticated, much more arbitrary connections to match kind of things we want. Cool. We're going to see some examples in a second about what is Chisel versus Scala, but questions at this point? Okay, let's see some Chisel versus Scala. Um, so this is almost the same module we saw in the last lecture. We added in one additional line. So rather than directly connecting the XOR gate to the output, we instead chose to put it in the val. So in this diagram here, just one I drew manually, we can see the hardware module, right? So we have the XOR gate, the inputs, and the output, as well as in blue, we can see the Scala references, right? So Scala, of course, all these vowels, these are references. And so we can see, for example, when we create IO, this bundle, which you can treat as boilerplate, is kind of like declaring a struct, right? So, okay, so this is a Scala reference, IO, and then, of course, we populate that with, references A. So reference A is going to be a reference in Scala, and what does it point to? Connect equals something. It points to a chisel object. In this case, a IO input of type bool, right? We can see the same thing for val B. We have another Scala reference pointing to a chisel object for an input, IO input. Okay, great. Val C is going to be an output, so we have that arrow going the other direction. Okay, great. Um, then what happens? Then we go ahead on the right side. We have an XOR, right? We have A XOR B. So that creates this XOR operation. The chisel library automatically, based on the ways it's set up, is, oh yeah, I'm XORing A and B, so I'll go ahead and pull in A as an input, pull in B as an input, and then do the XOR operation. But now I'm assigning this to a Scala reference, right? So that's what this mygate is. So mygate is not going to appear in the hardware. Mygate is something inside Scala, right? This is a Scala reference to a chisel component. And that's why later on, I can use that reference for this last line. When I have the output, I connect it to mygate. So mygate is this reference, and that goes through. So now this is one operator for chisel should be aware of is this colon equals. That's a connection operator. The connection operator takes whatever's on the right, takes the output of what's on the right, and connects it to the input of what's on the left. And notice that the colon equals for connection for chisel is different than equal for Scala, right? That's a different operator, a different purpose, and that distinction is important. Let's go ahead and see the Verilog for a second. And we can see, yes, the Verilog is what we expected from before. Our output IOC is, the XOR of A and B. So this mygate isn't even visible, right? But we can kind of still see this and kind of still play around with this, right? For example, let's say I forgot to do colon equal. What's going to happen? Well, it's going to tell you reassign to a val, right? Once again, val saving us, right? In Chisel, you don't want to reassign variables to change them. You want to connect them, right? So connecting is what you want. Now, let's say I was really stubborn and forgot that, and then said, no, I want this to be a var. Bad things, right? What happened here? What happened here is uh, io.c isn't properly set up. We can kind of see what happened, right? So originally, io.c pointed to a chisel output object. By making this a var and then reassigning it, I now have C pointing directly to the XOR gate. And so now this output object is kind of floating in the weird state. And so the tools are self-checking themselves, say, hey, wait a second, you have this IO port that's not set up right, and it flags that. That's the tool saving you. But once again, like I said, if you, number one, not just use a connect operator, but also just never use var, don't have that problem. It'll tell you before. So yeah, so whenever possible, we're basically all the time, use val, and it'll help save you. This is the most mind-bending part of the course right here in lecture 3. So take any questions people need. The big picture here is, this is a Scala program, and we're, instantiating chisel objects, right? Instantiating inputs, instantiating outputs, instantiating an XOR gate, and then connecting them together. So just being aware of thinking about, okay, what is the hardware I want to build? And then what programmatic steps I want to take to actually instantiate and connect those things together. And yeah, I mean, you can, of course, imagine if I want to do this directly like we had before, that's totally fine. Same hardware. Yes, I saw a question. So the question for recording is, why would I ever use a var for something like io.c? Something like an IO, I can't imagine a scenario where you want a var. The handful of times in this course where I would say a var is not out of question are involving loops. So depending on how you set your loops up, there's a way in functional programming to do loops where it's all immutable. But sometimes using a var, i.e. mutation in a loop, makes things a little bit better. But outside of loops, I don't really see much need for var. And like I said, you can write really great designs, kind of a fun flex for the students in the class to never use var the entire quarter. You can complete every lab, every homework, your own project, never using var. So if that's how it appeals to you, more power to you. I would do that. I spent 2 years as a postdoc writing a lot of Scala code to work on Chisel. And yeah, that code for fun for 2 years, I didn't use var. And you can do that. And it made it Interesting. There's a handful of times where the var makes it cleaner. If it doesn't make it cleaner, I would not use the var. Good question. Okay, so with that in mind, we were just saying that, okay, that, from the headline, Scala values with references to chisel objects. What if I want to actually have more parameterizability, right? More flexibility. Well, what if I want to have a assignment thing I can do arbitrarily in chisel, right? Something called a wire. So a chisel wire is quite similar to a Verilog wire, right? It basically says, hey, here's a piece of hardware, and I can assign both its input and its output, right? Connected up. So here's our same XOR from before, but rather than doing everything directly, we're now declaring my wire. So we're using this wire type from chisel. So we get this wire object. And then we connect the output of the XOR gate to the input of the wire. That's what this connect statement here does. And then we connect the output of this wire to the input of io.c. So we're still going to get the same hardware. In this case, the chisel optimizer, recognizing this wire never changes what it does, can just kind of align it and inline it together so that Verilog is literally the same. But bigger picture, we have this ability to kind of flexibly assign things. And so you may say, well, what's the point of this? We'll show you an example in just a minute where we use wire to change what's connected to. But for now, you're going to see an example of wire being used. Cool. Questions so far? Okay, so then let's go ahead and see when's the situation we might want to assign a wire. And we'll do that in the slide after this slide. So what are we doing in this slide? There's something called a chisel when. So this is like a mux. It's a different programming construct, but the types of places you use it are very similar. So what a when does is it's a when condition and then a code block. So when this condition is true, and this is a chisel condition, this is not a Scala condition. This is in hardware. Make whatever is in this block true. Make whatever do whatever's in this block. So usually it's connections, so make those connections. And of course, also an else case. And so you can do that as well. And so sometimes people find using, when and otherwise. There's also an else when for a other scenario where you can kind of. So this is like an if else. If you want a if else and then if on that else clause, that's when the else when is for. And so depending what you're doing for a simple one-liner, you may find the mux syntax from earlier today's lecture is more convenient. But as you'll see, you have more sophisticated designs. You actually prefer to have maybe these when blocks, and you'll see more examples where they make more sense. But in this case, we're just doing a mux. And so chisel on its own is going to turn this into that ternary statement just fine. Like before, this is parameterized. I can change the bit width, no problem. Now let's see some scenarios, play around with this when statement, right? Let's say, for example, I only wrote a when and didn't give an else case, right? An otherwise. It's going to yell at me because uh, it's checking. The tools are automatically checking and said, hey, you know what? I don't know what value out has at all times, right? I know when io.s is true, it's going to be connected to io.in, one. But otherwise, when this is not the case, what the heck should it be? So with the otherwise case in this example, yeah, you can see for all possible values of io.s, io.out has a connection. And we'll see in just a minute, let's say I didn't do it this way, but instead did this. This would also work. Because in this case, io.out always has a value, in this case of in0, and then I'm conditionally changing it in the case of io.s, and you can see that, yeah, the tools are making that conditional happen with a mux. So when's a way to kind of have this functionality in hardware, and there's a lot of times where you'll see using when, especially when you're connecting multiple things inside these blocks, that's less cumbersome than using the mux statement. This example is trivial, so it's only one liner, In this case, I would use the mux statement, but when you see real hardware, you often have multiple things kind of changing together in tandem. That's when this becomes helpful. Cool. Okay, let's go ahead and restore things real quick. One other interesting aside from a language point of view, people often comment that this dot here is confusing. Like, why is that there? That's one of those wrinkles from Chisel not being a proper language, but instead being embedded in Scala. It actually turns out that what's happening is this is actually a function call, right? This is a function call. There's some arguments here. This is another kind of argument. This is a following function call. So actually, in Scala, you can remove periods from function calls, and it'll do the right thing. So why did I put the dot otherwise in there? It turns out when you write Chisel code, for reasons I'm not enough of a PL person to tell you, 98% of the time, you can leave that dot off. It'll work just fine. But at 2% of the time, it's going to give you a really weird error. And you're not going to know what it is. And so that's why you can just put the dot there always. And so yeah, same for else when. It's kind of funny, this language, right? For a lot of things, you can just leave that dot off and it does the right thing. It calls a function. So you have like, object space method name is another way to invoke a function, which seems like an odd way to write a function, but you realize unless you get very native looking embedded DSLs, is why they have that functionality. Cool. Okay, let's go ahead and now bring that wire back in, right? So this is referred to as last connect semantics, right? So your program's running. We saw the diagram a second ago, and you have connections. And so when you make those connections, maybe I'll go back to that slide first. Um, Understand that even though I have all these things as vals, that's these Scala references. So my wire, for the entire lifetime of my wire, it always points to this chisel object. However, when I make this connection, this is actually modifying the object, right? So my wire is still a val, not changed. It's still pointing to the same thing. However, the chisel object itself now has been modified, right? Has its input connected to something. Um, and likewise, this final line here, io.c is now modifying io.c's input to point to something else, right? So just because something's a val, it doesn't mean the thing is pointing to can't be changed. It just means, in fact, what is pointing to can't be changed, right? So if I have a val x, x always will point to the same thing, but the thing I'm pointing to, that itself can be internally immutable. These chisel objects are internally immutable, right? Whereas we're connecting things together, that's changing the internal state for these chisel things. Okay, so now coming to the last connect semantics, let's put all this together, right? Make sure we're not running out of time. Oh, we have plenty of time. What do we have? So it turns out, you make these connections, you may have the case where the same object is connected multiple times. So the question is, okay, well, is W going to be connected to this constant 1 or is constant 7? And the answer is, it depends. And this is the last connect semantics. Whatever is the last connection that'll be evaluated, that's the one that quote unquote wins. That's the value it's going to have. So in this tiny little example, right, W is set to have the value 1 always. And then I use a when statement to sometimes, based on I to x, set to 7. So of course, the tools are going to be smart to kind of go ahead and use a mux for that. And once again, connect it up, right? Okay, so based on I to x, if it's true, we get 7, like the when statement kind of implies. And if it's false, we have the original value of W. So which of these connect statements wins? Well, it depends on the value of I.x. And so you saw an example a minute ago, I did the mux that way. This is a very helpful thing where you kind of can set a value for something and then kind of conditionally change it when you need to. Cool. And yeah, you can imagine all sorts of things, right? So of course, if I don't have the when statement, it's just always going to be 1. Oops. If I don't have the default value, it's going to yell that it's unspecified. I need to have all cases specified. And so yeah, so rather than doing else when, sometimes it's easier, or otherwise sometimes it's easier just to kind of give a default value and then conditionally override. And notice how, once again, W is a val the entire time all these things are happening. The val W is not changing. It's always pointing to the same chisel object wire. These connect statements are changing the internals of that wire. It's either pointing to the constant 1 or later on it's pointing to this mux construction here. Cool. Questions? Yes. Question is there a situation where you should use wire versus an int or a bool? So a wire is a physical thing, right? I'm saying this is a wire in my hardware design versus an int or a bool is a type. And so a type is, I don't know the right word, maybe intangible, the way to kind of think of it, right? It's like, and so a wire can be of type uint. So wire, because it's hardware, needs to be of a chisel type. So it can be of type uint, it can be of type bool. If I have a Scala int integer or a Scala, Boolean, those are going to be not able to be put into a wire unless I cast them. So the wire is a physical thing, and then the type is a, property of that if you want to think of it that way. Yes, correct. Yeah. So absolutely right. Great point from the audience. Yeah. So wire can change over time, 100%. So even though what I'm doing in the program is I'm changing what wire is connected to, the value in that wire is going to depend on the hardware that's operating, right? So that's why I said earlier, we have like simulation, for example, the hardware topology is going to be static. That's going to be fixed. The wire is connected in certain ways. However, as values flow in from simulation from the inputs, they will change the values as they go through the system. So the actual numerical values on these wires may change, but the connectivity will not change, right? That's kind of what we're doing. So it's good to kind of keep talking this over. Understanding, okay, what is mutable versus immutable? What changes when? It's a good thing to kind of have these conversations. Cool. Okay, so then let's use last connect to do something like making. Oh, another question. Sorry, go ahead. Great question. So for the wire, when you connect it, how do you can choose which side is which? The connect operator has a signedness to it. So this takes the output from here, gets its input of here. So it takes the right side output and gets it the left side input. That's the rule. Yes, it's always changing the thing on the left. So when I call this connect W to 1U, W is the one being changed. And now it's input connected to this, literal one. Great question. Yeah. So if I flip this, what's going to happen? It's definitely going to yell at me, and we'll talk about why. Um, so this connection is not a bidirectional connection. Wires normally are bidirectional. From the programming language point of view, it's not, right? In the sense that taking the output of W and it's connected to a constant. And so a few things are going to go wrong, right? I'll run the code first, but a few things are going to go wrong. So first, this is a constant literal, right? So constant literal has no input. It's an output only. So that's what the warning's telling us. The other thing that's going on is that now I'm connecting the output of W to this. W's input is unset, right? So because W's input's unset, and because this when only sets W some of the time, if we didn't have this error, the other error we'd be having is from before, which is W's not fully initialized, right? We need to know for all cases what W is going to be. So when you have a when, you need to be asking yourself, okay, I have set a conditional set of connections. What is the alternative? So either you get to have like a otherwise, an else when, or just a default connection. Good questions. Ask that again. Which one would be the var? You can use a var anywhere you can use a val. So the var val distinction is not here. So like I said, it's this kind of subtle point with Scala, right? Where you have a val, which is a reference to something. Because it's a val, you can't change what the reference points to. It always points to the same object. The object itself can be internally changeable, can be internally mutable. So in a few weeks, we'll start talking about collections. There are collections that are immutable, like once collection's made, you can't change what's in it. And there are other collections that are mutable. You can have a val point to a mutable collection and change the contents, which surprised some people, right? The point is the val itself is immutable, but the contents are mutable, right? And so these chisel objects, it's under the hood, we can see things in that diagram I drew about we're connecting inputs versus connecting outputs. That's changing the contents of these chisel objects. So even though we have a val point to these things, the chisel objects themselves internally have some mutation to them. Great. Good questions. Okay. So then Let's put this to work and do something useful, like, once again, doing absolute values. So we saw earlier in the lecture I had this with a mux. Now let's go ahead and do it with a when statement. So we can kind of see how this works, right? We have our output, the absolute value of x is the input, absolute value of x is the output. So normally it passes straight through. In the special case where x is negative, less than 0, we negate it. So it's going to get turned into a mux. The reason why the Verilog is a little more verbose than we might expect is because that is the syntax in Verilog for signed operations, and we did declare these to be signed. Um, these are essence, right, is the type. But if you kind of squint and ignore the signedness, you can see that, yeah, it's a mux, right? There's a question mark and the colon. And so that's the one statement kind of pulling through. And so you see this one statement allows for, very convenient, very clean code. And we'll keep building on it the rest of the quarter. Cool. All right. So then um, you may have noticed, before we've had this notion of, oh, I have, these W-bit buses going around. I have a W-bit uint. Um, what about whiffs and chisels? So Chisel has this entire engine that runs to do bit width inference. So if you don't specify how big something is, it will figure it out on its own. And that's why I was showing you that cheat sheet earlier. I don't know if it's still here. If you're curious what the rules are, you can see what the rules are, right? But uh, let's just run this code on the right. So for example, you'll see in this case, I specified the inputs are both of W bits. I didn't give a width to the output. However, the rules for addition is that it truncates, right? So if I go to that thing, let's go ahead and find the add operator. Here it is, addition. Um, it is the maximum width of either input. For now, let's assume I have two n-bit numbers, right? If I have two n-bit numbers and I add them together, because of the number getting bigger, technically the output could be n plus 1 bits, which is why I keep saying it's truncating, is because by having an n-bit input and adding it to another n-bit number and then getting a n-bit output, potentially there's a truncation possible, right? So maybe you don't want truncation, right? Maybe you want to make sure you get every bit. In that case, there is another add operator, right? So the add by itself is truncation. If you want to make it very clear as truncation, we use the division sign, right? The mod sign. Yeah, it's still truncating. If you want to actually make sure it grows and doesn't lose anything, then we have a different add operator. So now in this case, it's going to automatically grow the output size to make sure it handles that. And that way it does the thing you expect, right? And so, yeah, it'll infer these whiffs based on the rules kind of we're talking about. These solving these whiffs can be across modules and such. Now, if I go a little bit too aggressive on not specifying whiffs, eventually it will yell at me. For example, if I say one of these is undefined, it's going to say, whoa, 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 whoa. Like I know A is W bits, but I don't know how big B is. So because I don't know how big B is, I can't figure out how big C is, right? Um, but you'll see in a lot of these designs that as long as you have enough places the whiffs are set, the solver can figure out the inferred whiffs. Sometimes you know for sure where you want a certain whiff, you can specify that exactly. But as a general programming practice, if you keep specifying whiffs everywhere all the time, you have the theoretical risk of sometimes misspecifying that, right? So the bug could be not the code, but in fact you specified the width wrong, right? And so why take that risk, right? Why don't the tools do it for you? And so when possible, I like to not specify whiffs, assuming there's enough information there for the tools to kind of infer the whiffs for us, right? And of course, if the whiffs need to be changed, it has to do, extension, right? So for uints, there's zero extended. That means it puts zeros in front. If it's an essent, it's sign extended because it, wants to maintain the signedness, etc. Cool. Questions on that? Yes. So the plus percent is the truncating addition. So technically plus and plus percent are the same, and they kind of included both for symmetry. So if I go to our cheat sheet, maybe I can zoom in somehow. Yes, I can. Yeah, you can see that both plus and plus percent have the same operation of addition and the same width behavior. The addition with the and sign also is addition, but you can see it has this notion where it grows. It varies in operation, right? For example, multiplication, and these are kind of arbitrary choices that were done by debate by committee, because, for example, multiplication does not lose any data, right? Like it by default does grow. But it's a case of addition with the possibility of overflow is so common that they chose to make the default truncation. But if you really don't want to truncate, you can do plus and. So Verilog is a little interesting on this. So Verilog, you do plus, it does grow the output, right? You get that extra bit. However, if you connect it to something that's the same size, it silently drops it on you, right? So depending on what you want, it's similar, right? But in this case, this will be truncated from the beginning. This explicitly truncates, and this explicitly grows it. Cool. So like I said, you can tell already you're getting pretty far into the weeds, and that's the point, is that you guys have already learned after just a couple lectures to do combinational logic in Chisel, comparable to do in Verilog, right? You've basically learned most of the combinational logic. Only a few more details left. Let's put this to work. Let's go ahead and build a conversion module. It's going to take sign and magnitude. Remember, sign and magnitude is when I have a number, I say, here is the value, which is the magnitude. And I have an additional bit I float around with it, which is a bit, if it's 1 if it's negative, and 0 if it's positive, right? That's the sign bit. And so I can go ahead and convert that from sign and magnitude encoding to two's complement encoding, where it's a single, number altogether. And so how does this module work? Well, if the sign bit is 0, so let's actually say if the sign bit is 1, we got to do some work. If the sign bit is 0, that's the else case. The otherwise, the number is just the original magnitude, right? Now, if it is negative, the sign bit is 1. If you remember two's complement math from your undergrad, you remember you have to negate the number, right? So take the Boolean inverse, bitwise inverse, I was going to say, sorry, bitwise inverse, and then you add 1 to it. Cool. So how to look in hardware? Well, we're going to compute the two's complement, negation, and then based on the sign bit, either use that negation or just take the original number and prepend a 0 on it. The reason why I prepend a 0 is we set our output is going to be W plus 1 bits, and so that's the tool is kind of automatically filling it in. It's a uint, so uint is 0 extended. Cool. Let's go ahead and keep playing around with bits. So some other operations you may want to do in combinational logic. Maybe you want to grab a range of bits. You have like an n-bit uint, and you only want a subset of those bits. You can do high, low. You can even do a single bit at a time. That's really convenient. One oddity, which is a very long story to explain, you can't put this on the left side of a connect statement. So when you connect a uint, you're connecting all the bits at once. You can't connect only 2 bits of a uint. It's a very peculiar limitation. Verilog does not have that. Super modern Chisel allows that, but Chisel 361 that we use does not allow that, and there's a long story for why. But as annoying as that sounds, you'll find out it's actually not as neat as you might think. But yes, you can definitely say, x of 4 equals something in Verilog, and you can't do that in Chisel. But we can work around that. So yeah, you can definitely grab numeric ranges. You can combine 2 different numbers together. This is depending on the wires. Okay, I want all the wires from one, then all the wires from another one. Sure, that's a cat or concatenation. Or if I want to take a wire and repeat it, n times, I can do that as well. So to kind of see examples of all of this, we're going to do sign extension, right? So for sign extension, what are we going to do? We are going to find the sign bit, which is the most significant bit. So if I know my input is Wn bits, Wn minus 1 is the maximum index. Great, it's a sign bit. The extension is however many bits I need beyond what it is. Whatever my output bit size is versus my input bit width, I need that many more bits of the sign bit. I want to repeat that sign bit that many times. That's the fill. And then put these 2 together for cat statement, right? So, for example, if I have a 4-bit number and I want to sign send it to a 8-bit number, here we can see it. And you can see it's kind of materialized in Verilog as well. We have the sign bit is the most significant bit. We have the extension, and so this is the filling. In this case, it's choosing to do the filling with actual constants. Sometimes the Scala tools, the Chill tool is smart that can do the backtick that you have in Verilog. And then here's the concatenation, which in Verilog is, the braces. So it's concatenating these 2 together. And yeah, this is, parameterized block, very convenient. So I can, change these numbers arbitrarily and, it does the right thing, which is pretty handy. Cool. You might also notice that we, for the first time, have some assertions here. Since we have so many parameters, it's important to make sure our parameters aren't bogus. If I say I have a -1, you know, with input, that's doesn't make sense, right? What's -1 bit width, right? So sure, I should make that be, you know, greater than 0, because even 0 is not clear what that should do, right? It's still going to fail an assertion. When I do that, sometimes it kills the kernel, so don't kill the kernel. That's a Jupyter thing, not a Scala thing. Oops. Yeah, I have to go reset my entire workspace. We can do that. Um, oops, going back to the loading page. Okay, and now, yeah, so that was a really painful assertion violation, right? Um, Likewise, if I have a 2-bit input and say I want a 1-bit output, that's not very clear what that means for sign extensions. So I'm once again going to break my kernel by breaking the assertion once again. But we can restart our kernels and be fine. Cool. So yeah, assertions are really helpful. Turn things into, automatically checked rather than mistakes. It does make sense that we should, have an input that's at least 1 bit. That way we have at least a signed bit to grab onto, and the output should be bigger than the input. Although this one, I think it'll work fine if I make it the same size. Let's see. Yeah. Oops. Oh no, it's complaining about the 0-bit wire. Sometimes 0-bit wires are fine, and other times this case it's not happy. So in this case it does need to be wider. Cool. Okay. Other questions? So that's the end of this content. To give folks the roadmap, later today I'll be posting Lab 1. That'll be due on Tuesday night. Usually I have a full week this time because I'm heading for the lecture material. I didn't see the need to posting it too early. Like I said, Lab 1 will be done in Jupyter. Those here enrolled in Santa Cruz can you can upload that. You can download the Jupyter file when you've finished it and upload it to Gradescope, and it'll get auto graded. You can see them score right away. By right away, I mean within a few minutes, of course. But for running, I really recommend using that binder instance. It's a little bit finicky with the binder. Remember, it takes a little bit of time to start up, and then additionally, if you walk away from the computer, it might time out. So make sure you periodically hit the download button to save your work. That'll be the lab. There'll also be a homework one. That'll be due a week from tomorrow, so next Friday. So you'll have that posted tomorrow as well. You have a whole week to do it. That'll be more involved, longer assignments, that sort of stuff. And of course, yeah, welcome to the course. We're happy to have you all here. Next week I might need to move my office hours from Tuesday to Wednesday, but normally it'll be on Tuesdays. But otherwise, yeah, keep an eye on the Slack for this kind of announcements, and welcome and have a good weekend.